So now we have several practice questions dealing with the ideal gas law. The first one is not obvious, but it's related. So as in a game at an amusement park, you are supposed to knock over a wood block. You're given a choice of three objects with the same mass: a bean bag, a super ball, and a piece of sticky clay. Which object would you pick to most effectively knock the wood block over? You assume that each one has a given mass. You assume that you could throw it with a particular velocity since the masses are the same. And so the question is, which one will basically give you the largest force? And the answer, which is again not completely obvious, and it's related essentially to the ideal gas law, is if you have a wall and you have, let's say, in this case, we're talking about a block of wood, say, and so this has a particular mass with some velocity. The largest force will give you, because again, the impulse is just the force that's applied to the object times delta t, the time of the interaction. That basically just gives you the change in momentum. So, it's P final minus P initial. So if you imagine essentially where a beanbag comes in and it sort of, or a sticky thing, it comes in and just sticks to the wood, then the idea is that the initial momentum is here, but the final momentum becomes zero. Whereas if you have the same wood block, but now you have a super ball, which has a mass m, velocity v, but now the idea is it comes in and collides off. The idea is that now it's coming off with exactly the same v, and so assuming that it collides elastically. And so assuming that the time of the interaction is the same, in one case the change in the momentum is just equal to mv, it comes with mv and goes to zero. In the other case, delta p is equal to twice mv. And so what it means is that since you have twice the momentum transfer, that means that you have twice the force of interaction on the molecule, or in this case, the beanbag or the super ball, which means, by Newton's third law, that the force that the beanbag or the super ball exerts on the wood block is twice as large. So in other words, what I mean is that the change in momentum, the super ball will exert an impulse which is twice as large as either the sticky clay or the beanbag. And so the super ball is the right choice. So it's C that's the appropriate answer. Now, the second one is a carbon dioxide molecule is 11 times more massive than the helium atom. If you put 1 mole Avogadro's number of carbon dioxide molecules and 1 mole of helium atoms into identical steel 1 liter, 1,000 cubic centimeter containers at room temperature, 300 Kelvin, the pressure of the CO2 gas inside the one container will be either smaller or the same or larger. And this is basically getting back to what does the ideal gas law really tell you. And this is one of those very fundamental results, in that if you have n moles of a gas, or the other way of saying is if you have n molecules, and it doesn't matter what the molecules are, then basically if you have the same number of molecules or the same number of atoms, no matter what they are, even if one is much more massive than the other, the pressure, if the volume is the same, the temperature is the same, then the pressure has to be the same. And so what that means is that the pressure is the same for the helium gas as it is for the CO2 gas, even though the CO2 is 11 times more massive. This is actually kind of confusing when you think about it, because for the second one, is the related one, is that the carbon dioxide molecule 11 times more massive than the helium atom. You have a sample of air at room temperature that contains both carbon dioxide molecules and helium atoms. Compared to the speed of the helium atoms, it talks about carbon dioxide and so on. What it means is that, again, you have the translational kinetic energy for every atom is 3/2 kT. So every atom has basically, that much kinetic energy. And so effectively, if you look at it, if you want to isolate what the speed is, the factors of 2 will drop out. And so what you end up getting is that it's just 3 times Boltzmann's constant times the temperature divided by the mass of each individual molecule. Now, since what that means is that if you got a CO2 mass, it's much larger than for a helium mass, and that means effectively is that the velocity it decreases. And this makes all sorts of sense, because what it means is this comes back to essentially the issue about the CO2 and the helium containers of gas. The pressure is the same for the helium gas because effectively each helium atom moves more rapidly than the CO2 molecule. And so what it means is that each one is creating just the right velocity to get the same momentum transfer per collision, effectively. So in other words, it creates the same amount of pressure. It's not the same momentum transfer in general. You'd have to work it out. But they effectively have the same kinetic energy. I'm sorry. And so the idea is that the kinetic energies are the same for a helium atom or a carbon dioxide atom. And when you work it all the way out, when you consider basically the interaction time with the walls and the momentum that they transfer, the pressure will be the same regardless about what you have, heavy atom, light atom, or whatever. But what's certainly true is that the carbon dioxide atoms move slower, molecules move slower, and so it's actually B in this case. So this covers all the material, and so when we get into Tuesday's lecture, we will basically cover a good fraction of all this material.